This is the sixth lecture on Lagrangian mechanics. In the fifth lecture, we have seen that the most general form of Euler-Lagrange equation, when the force acting on the system is partly conservative and partly non-conservative, is this: the where the conservative part of the force is represented by a potential which has been included within the Lagrangian T minus B, and non-conservative part of the force is represented by the generalized force. But if we can represent the generalized force, the conservative part of the force with also in terms of generalized force, but in that case it simply reduces to a equal representing the force via P. We now where the generalized force is given by summation over I is equal to 1 to n Fi dot del Ri del Qj. Here we consider a special type of non-conservative force, which is the dissipative force or frictional force. Say for example, consider a particle descending down the air, and air offers a resistance. The resistive force that is offered is proportional to velocity. So we consider the dissipative force like friction, dissipative force like frictional force, which is proportional to velocity. Recall the Stokes law. Stokes law in viscosity, that is when a spherical body descends down through a viscous fluid with terminal velocity, the resistance, the viscous resistance that is being offered is proportional to velocity. This when the resistive force is proportional to velocity, we call this is the Stokes law. So we consider a special type of non-conservative force. This is the dissipative force F. This is the FID. This is the frictional type force. It is the velocity dependent force. So we write this Vxi j cap ky Vyi. This is the force acting on the ith particle. Now we can write it in terms of a function called the Rayleigh dissipation function. This is Rayleigh dissipation function is defined as half summation over I, sum over all the particles, kx Vxi square ky Vyi square plus kz Vzi square. So if we differentiate it with respect to V, so that is del R del Vxi is equal to kx Vxi. So with this spirit we define a gradient function with respect to the velocity, where R is this, and we have, if we write this as, this is I cap del L Vxi plus j cap del L Vyi plus k cap del L Vzi. This is written for this part, and this operates on so that this part becomes Fd pointing on I becomes, when this operates on this, only this part continues. This becomes I cap kx bxi plus j cap ky byi plus k cap kz bzi. So this is indeed the frictional force acts on the ith particle. So we can write the non-conservative frictional force as this. So what happens to virtual work done? So now we come to the case of generalized force QNC, which we write QD dissipative force as summation over I FID dot del Ri del Qj. Now for this part we write R. FID we have written it as this. On Rayleigh dissipation function, and this part is written as del Ri dot del Qj dot, which we have proved earlier. We have proved that del Qj del Qk is equal to delta Qj dot delta Qk dot, etc. And these are valid often for different bases. So this is nothing but the velocity. So this becomes simply, when summed over I, this becomes del R del Qj dot. So del R del Qj dot. So when we include this in the Lagrange equation, this becomes I am sorry, I made a mistake regarding the definition. This is defined as minus this, as because this force is a negative one, being a dissipative force, it is considered to be negative, and so up to this is a there will be a minus sign, and this will be a minus, there will be a minus sign. So if we can include this in this Euler Lagrange equation, this becomes ddt of del L del Qj dot minus del L del Qj plus del R del Qj dot is equal to 0, where R is known as Rayleigh dissipation function. Rayleigh dissipation function. One may also define a potential, U, the generalized potential or velocity dependent potential. Velocity dependent generalized potential. U, such that the Qj, the total force acting on the is given by del V del Qj, which takes into care the conservative part, and minus del V del Qj, which takes into conservative part, plus del R del Qj dot, which takes into account the dissipative force, and we write it as del U del Qj plus del U del Qj dot, where U is written as V plus R. So this is the generalized potential. And consequently, one defines the generalized Lagrangian L is equal to T minus U. This generalized Lagrangian indeed satisfies this equation. So what we have done in this class, in this sixth lecture, we have considered a special type of generalized or non-conservative force, that is the dissipative force, which as per Stokes' law depends on velocity. And for such velocity dependent potential, we have defined a special type of function called the Rayleigh dissipation function. That is, when we have dissipative forces present, the equation is given by two scalar quantities. One is L, another one is R. Sometimes it would be convenient to introduce generalized potential. In general, the potential does not depend on velocity for a conservative system, but for non-conservative system, the potential may depend on velocity. As for example, when dissipative forces are present, we can define the generalized potential U, which takes into consideration the conservative part of the potential V, as well as the Rayleigh dissipation function. And one defines the generalized Lagrangian, the cursive L, which satisfies this equation. This is the generalized Lagrangian L. Such a velocity dependent potential also occurs when a charged particle is subjected to electromagnetic field. We shall consider such system afterwards. Today, in the next part of this lecture, we shall apply the theory developed in this class to few simple problems. First, we consider a particle which is moving in a plane, in a plane, and is being subjected to a non-conservative force field. So if the particle moving in xy plane, the force acts on it is I cap x plus j cap y square. So what will be the Euler-Lagrange equation for this case? Now the kinetic energy part, T is equal to half m x dot square plus y dot square. This is the kinetic energy part. Now coming to the generalized force. The generalized force Qj is defined as summation over Fi dot del Ri del Qj. Since it is a system comprising of a single particle, this is F dot del R del Qj. Where R for particle moving in plane xy plane is I j cap y, and two independent variables q1 is equal to x and q2 is equal to y. So we write q1, the generalized force is, another thing is, so del R del q1 is equal to del R del x is equal to I cap, and del r del q2 is equal to del r del y is equal to j cap. So the first component of force, that is the q1, is f dot del r del x is equal to f dot I cap is equal to fx, which is simply x, and this is qx. Basically this is qx, and qy is equal to q2 is equal to f dot del r del y. This is f dot j cap is equal to fy is equal to y square. So we use Euler-Lagrange equation to this. First equation is for x component ddt del t del x dot minus del t del x is equal to qx. Since t does not depend on coordinates, this part is 0, and we have the kinetic energy is this, so this is this is ddt of mx dot is equal to x, or we have mx double dot is equal to x, and the second for y component we have which gives you ddt of my dot is equal to y square, or we have my double dot is equal to y square. These are exactly same equation which we could obtain from this Newtonian mechanics when written in component form. So this is a very simple example of Lagrange's equation when applied to a non-conservative system. We consider another particle moving in polar coordinates in a plane, and we represent the particle moving in polar coordinates r theta. So in r theta coordinate system, we are considering a force which is governed by a radial part, which is r cap plus b by r theta cap. So the particle is acted upon by two forces. If it is the x-axis, this is y-axis, then when the particle is over here, this is r, this is theta. There are two parts. One is the radial part of the force, which is this, and another one is the cross-radial part of the force, which is given by this. Now, if we want to represent this by the radial part, if we write the radial part of the force is AR, which can be written as del V, del R, then apart from a constant, V is half AR square. But if theta cannot be considered expressed in terms of a potential, because this is not radial, so its curl part is not 0. So that will be taken care into by the generalized force. So this part we write as minus grad V plus B by R theta cap. So QR is equal to B by R theta cap dot del R del R. Note that R vector is R cap times R, so del R is R cap. So this is B by R theta cap times R cap, which is 0. So the non-conservative part doesn't contribute anything to the radial part. So Q theta is equal to B by R theta cap dot del R del theta. Similarly, since R is equal to R cap times R, this gives you del R del theta is equal to R theta cap. So this is B by R theta cap dot R theta cap is simply B. And the kinetic energy part is half m dot square plus r square theta dot square, so which gives you Lagrangian L is equal to half m dot square plus r square theta dot square minus the potential energy part is half a r square. Then we have del L del R is equal to the m is missing, m r theta dot square minus a r del r dot is equal to m r dot. So the equation of motion for this is del dt of del L del R dot minus del L del R is equal to QR, which gives you m R double dot minus m R theta dot square plus AR is equal to 0. This is one equation of motion, the radial equation of motion. And for cross radial part, we have del L del theta is equal to 0. There is no theta dependence. And del L del theta dot is equal to m r square theta dot. And the equation of motion is dt of del L del theta dot minus del L del theta is equal to q theta. This gives you ddt of m r square theta dot minus 0 is equal to b. This is the transverse component of equation. So here we have applied the Euler-Lagrange equation to very simple cases. As the third example, where the dissipative force is considered, dissipative or frictional force is considered, we consider the projectile motion in air or a particle descending down under the action of gravity, where the air resistance is taken into consideration. So we consider a particle, this is the coordinate system, we choose x, y, z. Z is the vertical axis. We have a particle which is dropped from a height h and it is descending down. So at any instant, if we consider z is equal to 0 plane as the zero level of potential, then we have the Lagrangian is half m z dot square minus mgz, sorry, plus mgz, because when it is above the z, this is the potential. And the Rayleigh dissipation function, the dissipative force, is taken into consideration by the Rayleigh dissipative force, which we consider as k v is equal to, k v is half k v square. Actually the force is, dissipative force is acting vertical downward is k z dot and this is taken into consideration by the Rayleigh dissipation function half k z dot square. Recall that the equation of motion is ddt of del L del z dot minus del L del z plus del R del z dot is equal to 0. Where this is mz double dot, this part is mz double dot, this part is minus mg, and this part is plus kz dot is equal to 0, or the equation of motion is mz double dot plus kz dot minus mg is equal to 0. This side, sorry, this side is okay. This is the equation of motion along the when the particle is acted upon by a dissipative force. Here you note that the gravitational force acts downward while we have chosen the z-axis to be directed vertically upward. This is the equation of motion, and one can integrate this to get the value of z dot in terms of z and time. So this is the Lagrange's equation when applied to holonomic non-conservative system. In the next class, we shall first consider the Lagrange's method of undetermined multiplier, which takes into consideration the constraints when applied on a system, and then we shall finally come to Lagrange's mechanics when applied to non-holonomic system. To be specific, we shall consider those non-holonomic systems for which the equation of constraint can be expressed in terms of Pfaffians.